Hello everyone, good morning and welcome to this presentation, Artificial Intelligence for Optimization of Mining Processes. My name is Rodrigo Andai. I am the Global Mining Leader for Honeywell Connected Industrial. Today, I'm going to tell you about our experience as a team in developing and implementing a machine learning system for mining industry, along with reflecting on lessons learned and trends in the field for applicable for future projects and initiatives, with the view on increasingly widespread adoption of this technology and similar ones. So, a little bit about the agenda. The general agenda for this will start with the motivation on data as an underutilized asset, then a case study, the prescriptive system for the SAG process in a concentrator plant on a very large copper producer. From here, we will analyze the fundamental pillars that support the productive solution of this nature and the key focuses to ensure its sustained use over time, and finally, messages and reflections on artificial intelligence and machine learning. Quick question, are those slides passing okay, Dominic and team?
Yes, I can see the
perfect.
agenda slide.
Perfect. So, data as an underutilized assets. The people and process technology framework is a well-established methodology that seeks the balanced interaction of these three for greater productivity and efficiency. The digital transformation expands its triangle to four components with incorporation of data as an element that has to do synergy with the others. The key here is to distinguish the role of data as a valuable asset that can be put to the service of the other components. Organizations often invest in solutions and then try to adapt people and processes to the solution. But since the solution is to arise from people and processes, this doesn't work. Specifically, and this is very important, the question is not what to do with the data we have at our disposal, which is many times the approach, but what opportunities and needs we detect that can benefit from applications based on the use of data. Is data at the service of problems, not problems at the service of data? And this is where the strategy is key. The role of leaders must be to influence the culture of the company to make this a reality at all levels of the organization. Particularly in mining, there are terabytes and terabytes of data stored in data centers, and most of them are historicized and forgotten. The increasingly better instrumentation and in greater quantity only increases the amount of data that's accessed, but for the processing capacity and use of the same, it doesn't scale the same way. Most decisions are still based on personal experience of each employee in the company, and the analysis are usually done post-mortem or using small amount of data. And it's logical, even the natural restrictions of time and processing capacity that we have, it is not possible to carry out prescriptive analysis that will allow us to anticipate situations or optimize on large scales. So we limit ourselves to working in reactive mode. However, artificial intelligence and machine learning initiatives are being carried out in all of the large mining companies of the sector, and we will see a case study where we participate in the development and implementation of a system of recommendation for the SAG process. As I mentioned, the team developed a system of recommendations for the operations of the SAG process in large concentrator plant. This consisted of an application based on machine learning models for the delivery of actionable recommendations for the operations area, with a view on increasing the production of fine copper. For this, supervised and unsupervised machine learning models were developed that receive as variable inputs of control and plant context, and then, through an optimization algorithm, generate a list of recommendations for SAG grinding and flotation that was seeking to maximize fine copper production. The great added value was that the system was aware of the existence of an advanced process control layer that the equipment processed, and therefore it was designed to be a bridge between advanced analytics and advanced process control. So this is general overview of a diagram of the architecture. Let's dig into it. We start with the SAG process, consisting of 2 SAG mills with 2 ball mills each, in addition to a pebble crushing plant, and then the flotation process contemplating rougher cells, scavenger cells, and cleaning columns. The objective is to maximize the production of fine copper by suggesting actions on the control variables for this equipment. We separated the variables into operational variables on which we can recommend and act, and those of plant context, including upstream or downstream information, and feed them into predictive machine learning models. In particular, we use XGBoost for our predictive models, and we divide the SAC processes into grinding and flotation, training one model for each stage. The final output for the models, when cascaded, was that the fine copper was capable to be produced at the current plant context and given the value of operational variable data. Then it was passed on to an optimization stage based on Monte Carlo models with Markov chains that looked for the operational variables that will maximize the fine copper predicted by the models. Then it was translated into actionable recommendations that were reported to operational through an interactive front end where the graph of the plant context, time series, and variables of interest, operational limits, and suggestion for changes of the limits were displayed. These could be accepted or rejected through the interface, and when accepted, they were written directly into the advanced process control layer of the plant. Additionally, we incorporated a clustering model that will allow to do more functionality. Finally, a KPI dashboard was developed to monitor performance of the models and the use and adherence of the platform and reports on the productive impact. So we can see the important results. As the pilot was carried out to implement the recommendations of flotation models, we show an increase of 0.9% of recovery during the month of the pilot compared to the previous month. One important thing is that this was a previously optimized plant using advanced process control. So it wasn't, that there was nothing there. This was achieved through stabilization of the recovery in the different stages of mineral treatment, which was previously inversely related to recovery, decreasing with one mineral process. On the grinding stage, the process mineral base increased by 3.5% during 2019, driven by the detection of bottlenecks and piloting that led to changes in the operational standard, all based on the recommendation system. Let's go a little bit to the promise of potential and the achievement of the benefits. In our experience, developing models of this type were several points that we can identify as key to landing the process potential benefits that machine learning offered to us. If we start with the static data set with the few lines of Python code in a Jupyter netbook, we can show great potential of benefits in different areas of production. However, to materialize them, there is a great multidisciplinary work that needs to be carried out. In this figure, we show some of the important areas involved and some of the trends and characteristics that as a team will seek to continue working in for future solutions. The analysis of these points will be extremely extensive, so we'll see in a little more depth only those involved. On the data side, trends are to incorporate data cataloging systems to find out what we're looking for quickly, data governance to manage its availability, use and security, and data alignment that incorporates metadata describing the origin, movement, transformation, and characteristics of the data. Regarding ingestions, we must consider cleaning the data and quality checks to avoid saturating our data lakes with poor quality data, which will lead to poor quality analysis. It's useful to incorporate refined or pre-processed tables in addition to tables of calculated data features to facilitate and speed up the modeling work from them. On the modeling side, the key start with the why and be clear about the motivation behind a certain solution and the needs it attacks. Sorry about that. In order to continue to convince and give more confidence to stakeholders and future users. It is key to understand what systems each solution is built on, what role it plays, and how it interacts with the other components of the process, control systems, dashboard, other applications, operators, process engineer, production plants, etc. From productive solution, I'll emphasize the user experience, but it's also desirable to contemplate the governance of models, versioning them, robust service systems, and continuous monitoring of the platform's KPIs. Finally, in change management, the interpretation of the results, opening the black box that machine learning models tend to be, and involving users through analysis and gamification tools is key. As a team, our motivation is to complement APC applications by assessing all the human decisions that are critical to getting the most out of these applications. In particular, we still depend on humans for many tasks, such as setting operational ranges, tuning controllers, and setting optimization goals. The best decision for this task will come from evaluating historic results, plant and mineralogical context, process constraint, global optimization mindset, and awareness of the production plan. These decisions are typically made by process engineers, APC, specialist engineers, or operators who work in high utilization, multivariate, and high information frequency environments. We propose to use machine learning models to reduce the human load by providing adaptive tuning and optimal ranges for APC. In terms of user interface and user experience, the following are some key pillars to consider. The solution must show its value, ideally reinforcing the benefits achieved with its use. It must be useful. For this, iterative development with users is key. In our solutions, we incorporate mechanisms for delivery of feedback and comments. It must be transparent. That is, the better we can explain to users how a model reaches a certain conclusion or value, the more they will trust the results, and the better the feedback will be, which then can contribute to continuous improvement. More on this later. It must be accessible, so we must monitor as much as possible both the platform and the quality of the models we store in production. Lastly, it must be easily usable. When we first use mobile apps like Uber or Spotify, software or access social media pages will rarely require a more extensive tutorial than a brief description of features and components. If the interface requires extensive tutorials or training, it can probably be designed better. Sophisticated machine learning models often produce accurate predictions, but are known for their black box nature, which works against their adoption. A first attempt to understand how our models think is the relative importance of features used during training. The XGBoost library in Python brings a simple functionality to graph the importance of each feature, but can we trust this result? First, the function requests a metric for calculation, weight, cover, and gain. Unfortunately, the results are notoriously different depending on which one we choose to use. Worse, regardless of which one you choose, they're always consistent. We define the metric as consistent if, as the importance of the feature increases, the metric of the feature increases. This seems obvious, but in practice, it rarely happens. In a tree model like XBoost, the importance will depend on the order in which the variables make splits, biasing many times to produce splits lower down the tree and yielding inconsistent results. Additionally, this graph doesn't indicate correlation between features and target variable. A much better alternative is to use SHAP values, which allows us to explain incredibly detail each prediction of our black box model. Inspired by Shapley values, developing in the context of game theory in 1951 by Lord Shapley, winner of the Nobel Prize in Economics in 2012, which solved the following questions. In the collaboration of players, where a profit is obtained as a team and given different contributions from each, what's the fair distribution of the profits among the participants? These ideas were adapted to explain the importance of variables in each prediction made by our model, with the advantage that for the tree models like XGBoost, this solution is not even an approximation, but is it exact. In the case of networks, for instance, it wouldn't be the case, since we can never omit an input variable, and although the trees cannot do either, we can take it the sum of both branches of the split of the variables we're evaluating. In this way, and as a simple way in Python, through Python SHAP library, you can generate the following features in point graph. Each point corresponds to a prediction of our model. In this example, we see a test model which with data from tailing thickeners. In our training data set is 10,000 data. Each variable will have 1,000 points. Distributing the x-axis according to the importance of the variable that had in the prediction to generate the predicted value. We see immediately that these values can be positive or negative. That is, they contribute to increase the predicted value or decrease it. Additionally, it offers us the relative value of each of the observed feature, which allow us to identify correlation between feature and targeted variable. For instance, in the first feature, red and positive SHAP values indicate that when the feature takes a high values, it contributes positively to the predicted value. But when it takes low values, it contributes to predicting low values. So there is a positive correlation in all the values sections. However, we should not confuse the correlation it indicates with causality, of which the graph offers no information at all. If we now look at a particular feature, we can see how it correlates to the target variable through a dependency graph. However, the usual dependency graphs show the average values predicted for each value that's studied. Here again comes the advantage of using SHAP values. We have the contribution for each particular prediction, so we can see the dispersion in each section. For example, on the marked area, it's observed that for low values of the studied feature, there'll be a negative SHAP values for all predictions, which indicates an inverse correlation with the target variables. However, there is a great dispersion in this particular contribution of this feature, depending on the predicted point, indicating that there must be other variables probably related to it that influence how much it contributes in each case. The SHAP library again facilitates our work and graphs, and it graphs in colors the use of a second variable, one of the most closely related to one study, to visualize the effect described. We can see how for low values of the second variable, the SHAP values approach to zero, no importance, and for high values, it takes great importance and pushes the prediction down. In general, this is a great tool for analysis and validation of the models. Finally, we can study a point prediction and see how each feature contributes to reaching the value predicted by the model. We start from a base point, which corresponds to the mean of the target variable, or in other words, our best prediction in the absence of input features. The color arrows explain how it went from the base value to a predicted value, with the size of the arrow indicating the size of contribution. The SHAP values are additive, and therefore their scale and units are exactly those of the target variable. And the sum of the SHAP values for each feature gives us the value predicted by our machine learning model. Think about the importance of providing these values on graph for the prediction that our model deliver, in particular to users, to increase their confidence in the system they're using. And that's a fundamental part. Another important way of involving users with our solution is to provide analysis tools and environments to play with the models. Having a sandbox or a scenario generator where you can test what happens in if a certain change is made to variables can be very useful. In our experience, not all recommendations from prescriptive systems are always implemented, often due to external operating restrictions. In these cases, the prediction can be reevaluated in the scenario of implementation of a subset of recommendation, or trigger a new set of recommendations, optimizing only for the variables of interest. In general, the more we can gamify certain aspects of our solution, the greater the use that will be made of them. Another option is to offer complementary analysis for tools to our machine learning model with interactive model graphics and like the ones offered by Plotly. In particular, we have very useful parallel coordinate graphs to study multivariate systems, and they have been very well received by users in search of operating points. Another way of involving user with a solution is to provide analysis tools and environments to play with the models. Having a sandbox is useful. Here's an example of using this chart to identify operating ranges for a variable for a SAG mill. We can graphically filter to isolate the scenarios of interest and identify, based on history, favorable ranges for a higher order processing. As a last topic, I'll talk about technical depth in machine learning systems. As you can see in this figure published in an article for Google, the machine learning code is only a small part of a complex interconnected system that we must develop in order to have a stable, consistent, reliable, long-term lasting solutions. In recent years, there has been a considerable increase in interest in those topics, as advanced analytics and machine learning have ceased to be standalone analysis tools, and they have become solutions that need to be put in production with the standards that this demands. We already have mentioned several of the complementary systems during this talk, but let's talk more in depth a look on how to continue this, to strengthen our systems with incorporation of additional solutions and adoption of best practices. The development governance of models involve multiple concepts such as testing, validation, versioning, reproducibility of results, etc. We have used MLflow as a solution for this need, but there are many more and new ones that will continue to be developed. Some desirable features in our solution should be the following. In the development of our model, our code should be versioned in a repository, and it usually is. However, it is common in exploratory stages to do numerous experiments and tests. More than once it has happened that by testing combinations of hyperparameters and variables, we have found models that satisfies us, but by continuing to test, that successful combination was lost or was very difficult to replicate. Versioning of our experience was very useful, historicizing the aforementioned. We should also be constantly comparing with simple models and with subsets of data fitted with some criteria for validation and review of potential and unwanted biases. Regarding infrastructure, highlighting portions of good quality assurance or pre-production environment, and in monitoring, be attentive to any deviations in metrics to update quickly so as not to see trust if our system falls. An interesting test is to check the consistency between feature importance between each retraining. Sudden changes probably indicate instability in the model or high correlation between many variables considered. Data at the service of people and processes, seeking that solution that add value to the users. A solution that gives more work to the user than it has been beforehand doesn't work. It will not have a good reception, and the use will be poor. Our models do not exist in a vacuum, but are embedded in an ecosystem of solutions and systems which we must bear in mind and with which we must often interact. A clear example is the advanced process control systems. Always think about user experience and involve as much as possible in the users to the solution, explain the model and the results, using sharp values or similar techniques for exploration, validation, increasing confidence in the system. Finally, strengthen our pipeline as much as possible, thinking about development and continuous integration with the emphasis on good practice, protocols, and monitoring of systems. Thank you very much to all the audience and GMG for the opportunity, and I hope to have added some value to the audience. Thank you very much.
Thank you, Rodrigo, so much for this great presentation. We actually have several questions on the chat line, so let me go through them. So the first one is from Osvaldo, who wrote me directly. Could you please expand on the clustering model in the strategy? How are you handling the trouble and downtimes in operations with your model? What is the accuracy of your greening model?
On that, Osvaldo, it will be a long explanation, so we can take it offline. So I think we're written. But Osvaldo, I'll get in touch with you for that.
Perfect. Maybe something brief just for the rest of the audience.
Yeah, actually, it was a refining process. So as I explained, it started, very dispersed, and after several iterations, it tended to converge pretty well.
Okay, perfect. Thank you. I have a question here from Laura. Do you think it's reasonable to have a predictive model without having a MES system?
I think it is. Actually, as we mentioned here, this plant was already pretty well automated and with an advanced process control layer over the MES system. So it doesn't, to me, machine learning needs to be at the service, of an environment, and just seeking and trying to deduct information on data is not useful at all. Here, the recommendations were not to an operator to set up the plan, but an operator to accept a recommendation that goes straight to the advanced process control layer. So it wouldn't make too much sense to run artificial intelligence to a plan that has a MES system below.
Perfect. Now we have a question from Aiding. How could variables from plant impact negative? Is this mean is data has a problem? Do you have any real example?
I do. I mean, data from I can tell you one case that was a bottleneck we detected in this plant. There was an electronic ear on the SAG mill. An electronic ear was sending good data. It was noise data. However, when we did a machine learning analysis, we realized that although we were kind of optimizing for maintenance, the plant production was taken severely down by that variable. So that's an example of even good quality data was good. It wasn't an error, but it was negative impacting the plant. This is an ecosystem, so any variables need to be analyzed. And many times, putting a new sensor might not be good for the process. Too much sensing, if not coordinating, is not good. And the opposite case, if you have really bad data and you're using it, you can make the process fail miserably.
Perfect, thank you. Why the feed size distribution to SAG mill is not used? What are the manipulated variables in the flotation circuits?
There are many, and again, that's something I'd rather take offline with you, with the users.
Okay, that will be Osvaldo. Then this is a long question from Nicolas Orellana. What kind of technique you use to create the model rainforest, for example, and test, train, distribution technique? You made the prediction in real time or one time each. What format was the context data must be to be added into the analysis? How long it took to have the first good prediction and set trigger by PCA in real time? I don't know if you want to read through the question because it was a little bit long.
Yeah, but again, on that, there's several pieces of information on that I don't handle. So I was one of the hardcore ML engineers that was involved. But I'm happy also to take that to our team. But in general, in terms of real time, the decisions that were suggested here were operational points that were set up at every shift. So this is not a system that's adjusting set points every minute or online, but it's making a suggestion at the end of each shift, meaning it's not something that works online. It's analyzing data, and the predictions and the suggestions are done once every shift.
Perfect. What are the benefits of this implementation? What was the recovery improvement?
As it was said there, it ended up being close to 1%, 0.9% of extra, fine copper, recovered, which is pretty big, especially in a plant that was well optimized beforehand.
Perfect. And there's one last question from Nicolas, but I also, in the case that you don't want to share that where it was, it's okay. That it's basically where did this case study took place?
It was in a large underground mine in Chile.
Okay. Oh, and one last question, and then we're going to move into the other presentation. Thank you, Rodrigo. When the model recommends a change of a control variable in the process, will a process operator have to decide whether to accept the recommendation?
Yeah, what the model does, the way it's implemented now, it's not fully online. So it gives a recommendation, and the operator has to accept it or reject it. And also the model takes that into account. So there is a history of acceptance and rejections. I will try to analyze patterns as well to see, if there is some, operational, I would say, mistakes the model is making, or if there's some user that just not accepting a certain type of models. But the process is the following. Once every shift, you have the user interface suggesting some setup changes. And if the user accepts them, it goes directly, the acceptance modifies the set points and the triggers in the APC layer.